Hello, this is Dr. Hanaa Assil, and this is questions and answers on electrochemical cells. These are questions taken from the A2 Chemistry Edexcel, so this is Unit 5 of the A2 Chemistry Edexcel. Now, electrochemical cells, let's take a look at the first question. Label the diagram of the standard hydrogen electrode indicating the essential conditions associated with each substance used. Now, we should know that the electrochemical cell is made up of a half cell, and this half cell we need to first have its standard electrode potential. And we get that by using the hydrogen electrode as a reference. So the hydrogen electrode is made up of a solution of sulfuric acid with a concentration of 1 mole per decimeter cubed. You have to mention that. And then we have a platinum electrode inserted into the sulfuric acid solution. And we're going to pass what into this? This is the standard hydrogen electrode. So we're going to pass hydrogen gas. And you have to mention that this is at a pressure of 1 atmosphere or 100 kilopascal. The platinum electrode of the standard hydrogen electrode is coated in finely divided platinum, which we refer to as platinum black. Suggests why platinum is used as the electrode and why it is coated in platinum black. So in the standard hydrogen electrode, I have a platinum electrode coated with platinum black. Now we use platinum, of course, because platinum is inert, unreactive. It will not take part in the reactions. So we use that, and we cover it with a layer of platinum black because this allows larger surface area for close contact of the hydrogen gas and the H+ ions in solution. State the value assigned to the electrode potential of the standard hydrogen electrode. You should know that the standard hydrogen electrode is assigned a value of 0. So we have a list of the reduction potentials. The standard hydrogen electrode is given a value of 0. Explain why a reference electrode is needed anyway to measure the electrode potentials of the chemical cells. So if we have a chemical cell, why do we need a reference? Remember that if I have this half cell, for example, copper in copper ions, I need to connect it first to a hydrogen electrode, standard hydrogen electrode, in order to determine its electrode potential. This is because a potential difference requires a complete circuit. In order to determine the potential difference, the electropotential of the copper, for example, I need a complete circuit with 2 electrodes, current flowing through it. Then I can measure the electrode potential, or I can get a potential difference. Okay? Then this question says, sometimes the calculated value of the cell for a reaction shows it to be thermodynamically feasible, but in the laboratory no reaction occurs. Well, we should know that, first of all, for a reaction to be feasible, the E cell is positive. We're going to calculate E cells in a minute, and the E cell should be positive. Now, sometimes the E cell is positive, and that indicates that it is thermodynamically feasible, but actually it does not react. Now, why would this happen? If it is measured under conditions that are not standard. So remember that we're talking about cells, electropotentials that are standard. So if I'm doing the reaction at conditions that are not standard, that means the temperature is not 298 Kelvin, or the concentration of the solution is not 1 mole per decimeter cubed, then in that case, the E of the cell may be different from the standard electrode, the standard E cell, and that means it may not be feasible. Or maybe the E cell is positive, but the activation energy is very high. So we don't want the activation energy to be too high, or the reaction would not actually occur. Then this question says the half equation for an iron 3, iron 2 half cell is this. Remember that all electrode, for the standard electrode potential data in the data booklet, all reactions are reduction or gain of electron. The standard electrode potential of this half cell is measured using the apparatus shown. So of course, to get the standard electrode potential of the half cell, we connect it to a standard hydrogen electrode. And remember that each of these beakers is what we refer to as a half cell. We need to connect the electrodes using wires. So this is the connection to a voltmeter to determine the electric current. And we need to connect the solutions. So to connect the solutions, we use what we call a salt bridge. This is made up of a U-tube that is inverted into the solutions, and it contains a saturated solution of what? Usually it is potassium nitrate. So the salt bridge, which is the connection between the solutions, is actually a saturated solution of potassium nitrate. Now, electrode B. What is electrode B? Electrode B is the one in the solution of iron 2, iron 3. You have to remember that if my half cell is made up of only solutions, no metal is involved in the reaction, in that half equation, then the electrode has to be a platinum electrode. Solution C. Now we're trying to calculate the standard electrode potential of iron 2, iron 3 half cell. That means solution C should be made up of a solution of iron 2 and iron 3 ions. Actually, each of them should be with a concentration of 1 mole per decimeter cubed each in the solution. Then this is another question. Remember, we have tables like this in the data booklet, and sometimes the question takes part of the data booklet and gives you these information. So this question says vanadium exists in different oxidation states which can be interconverted using suitable oxidizing and reducing agents. Some relevant standard electrode potentials are shown in this table, and then the question is, write the overall half equation for oxidation of vanadium 2 ions to vanadium 5 ions, which is VO2 with 1 positive. So from all of this, we are required to write an overall half equation. For what? Oxidation of vanadium 2. So we look at this table. Where is vanadium 2? Vanadium 2 is that first or the second equation, which is highlighted there. So this is the equation that says V3 plus going to V2 plus, but we want to start with V2 plus. So we're going to invert that first equation. Remember that, I'm going to remind you again, if we invert the equation, we will then, after that, invert the sign for the E note. So instead of having the electrode potential for that reaction to be minus, it's going to be a plus. But for now, we're not talking about the electrode potential. We're talking about the equation. So first of all, he wants to start with oxidation of vanadium 2, and that means I invert that first equation from vanadium 2 to vanadium 3. And then where do we go next? We want vanadium 3 to go to something else. So that equation in the middle is vanadium VO2 plus going to V3 plus. I want it the other way around, so I'm going to invert it. So we invert it so that it is V3 plus going to VO2, two positives. So now we have V2 plus, V3 plus, and then we want to change the VO2 positives. We want in the end to get VO2 with one positive. So that is that final equation as it is. Or is it inverted? No, we need to invert it so that we end up with the required species. So these are the three equations. We put them on top of each other. And then, in order to get the overall, we need to cancel whatever is the same on both sides of the arrow. So you can see that the V3 plus in the first equation is after the arrow, in the second equation is before the arrow, so we cancel. And then the VO with two positives before the arrow and after the arrow, we cancel them. So we cancel anything on both sides of the arrow, and then we just copy what is left. So what is left? V2 plus we have 2 of the water to give the VO2 with 1 positives. We have 4 H pluses and 3 electrons. So this is the overall half equation that is required. Then the question says select from the table a reducing agent. So this is the same table that we had before. And we want to select a reducing agent which should reduce vanadium 5 to vanadium 4, but not to vanadium 3. Now, I'm going to remind you that the table is arranged so that the one on top is the one that is better reducing agent. So the one on top is the one that tends to lose electrons, and it will reduce anything below it. Remember that the electrode potentials are arranged in order of reduction potentials. So the one on top are the ones that have lower reduction potentials. They are the ones that will act as reducing agents and reduce whatever is below it. But anything at the bottom will not reduce anything above it. So we're looking for something that would reduce vanadium 5 to vanadium 4. Where is vanadium 5 to vanadium 4? It is in that last equation in the table. Now, I want something to reduce it, so that means anything above it. But I don't want it to reduce that other species to vanadium 3. Now, where is that? That is plus 4 to plus 3. I don't want it to reduce plus 4 to plus 3. That means I want something below that. So the one that would reduce vanadium 5 to vanadium 4 but not vanadium 3 would be the iron 2 ions. These are the ones that will tend to lose electrons. So we're looking at iron 2 going to iron 3. This is because its electrode potential is lower than that for vanadium 5 to vanadium 4. That means it is a better reducing agent, but higher than vanadium 4 to vanadium 3. So no further. Write the balanced equation. Write the balanced equation for the disproportionation of course, you know the meaning of disproportionation. That means a species is oxidized and reduced in the same reaction. So we want to write the balanced equation for disproportionation of course, we're using this same table that he gave me. So we want to change V3 plus to V2 plus and V3 plus again to VO2 positives, and explain whether this reaction is feasible or not. we look at the relevant equations in the table. We copy it if this is what we want, or invert it if it's the other way around. So I want V3 plus to V2 plus. Well, that's good. That's that highlighted equation. But then I want V3 plus to VO with two positives. So I need to invert that other equation. And inverting it means you invert the sign of the electrode potential. Now, to get the balanced equation, we add it all up. Remember, we have electron on both sides of the arrow, so we're going to cancel that, and we're going to copy whatever is left. So this is the balanced equation. Now, to get the E cell, we add up the E reduction plus E oxidation. And for this, it comes out to be a negative value. So remember, the reaction is feasible if the E of the cell is a positive value. Now, when we added this, it came out to be negative. That means the reaction is not feasible. Are we following? Okay, this next question says, which electrode and solution would be used to measure the standard electrode potential if I'm trying to get it for manganese 3 to manganese 2? Remember, we said if we're having only solutions in the half cell, then the electrode must be platinum. If we have solutions only in our half cells, no metal, we have manganese 3 plus, manganese 2 plus, then my electrode is a platinum electrode. What about the solutions? We said the solutions will have to be 1 mole per decimeter cubed with respect to each of the atoms. So 1 mole per decimeter cubed with respect to Mn3 plus, and 1 mole per decimeter cubed with respect to the manganese 2 plus. This question says potassium dichromate in acid is a laboratory oxidizing agent widely used in organic chemistry. Of course, we've used that before. Some electrode potentials relating to the use of this reagent are given. Deduce the ionic equation for what? Oxidation of ethanol to ethanol by potassium dichromate. So I look for where is the equation for ethanol to ethanol. Of course, it is the reverse of the one in the table. Ethanol to ethanol plus 2H plus 2 electrons. And then I want the equation for the dichromate to change into Cr3 plus. We add these up, but before we add them up, we have to have equal number of electrons. Now, if the one below has 6 electrons, I also want the one above to have 6 electrons, and that means I multiply by, what did I multiply with? I multiplied through by 3, so that all through we have 6 electrons on both sides of the arrow. I then cancel these electrons. I also cancel anything else that is the same on both sides. So let's go back again. We had 6 electrons, we're going to cancel them. But we also had 6H plus after the arrow on the first equation, and 14H plus before the arrow in the second equation. So we need to subtract these. So if I cancel the 6 on top, the 6H plus on top, then I have to subtract that from the 14, so the one below will have 8H plus. And then we add up whatever is left before the arrow and after the arrow. This is the overall ionic equation for the reaction. Are we following? Is this getting better? Okay. Then the question says calculate E cell, so we're still using the same table, for oxidation of acidified potassium dichromate of ethanol to ethanol, and ethanol to ethanoic acid. So here we're trying to calculate the E cell. Let us take a look at ethanol to ethanol. So the ethanol to ethanol, that is the reverse of the equation in the table. So we reversed the sign. Instead of minus, it is now plus 0.61. The dichromate to chromium ions, this is the same electrode potential. We add it. This gives overall E cell of plus. Please remember to put the sign. E cell has to have a sign, positive or negative. Then he wants the one for ethanol to ethanoic. So ethanol to ethanoic, again, that is the reverse of the reaction in the table. So we reverse the sign. And the dichromate, adding all both E cells, we have a total E cell of plus 2.27 volts. Then the question says, use your answer to B2. So where is our answer? This was the answer. The electropotentials for ethanol to ethanol and ethanol to ethanoic. Now, we're going to use that to suggest why it is necessary to distill ethanol directly out of the reaction mixture in the preparation of ethanol by oxidation of ethanol. Remember, ethanol is a primary alcohol, and we said if we oxidize it, it is oxidized to the aldehyde, but if we continue, it will go on to the acid. If we want the aldehyde, then we need to distill it directly. Of course, from the reduction potentials, this is because both of the reactions are feasible. They both have positive values for the E cell. But then, if you look at the values, you can see that the one for ethanol or ethanol to ethanoic is higher. So it is easier for the ethanol to go on to ethanoic. So I don't want to leave it, I need to distill it. The one for ethanol to ethanoic is more favorable since the E cell is higher. This question says the standard reduction potentials of two systems are given. What are the components of the half cell required to measure the standard reduction potentials of the iron 3, iron 2 system? Again, if I have iron 3, iron 2 system, then I want in that half cell which ions? I need both ions. Both iron 2 and iron 3 in my solution. And remember, we said each of them should be concentration of 1 mole per decimeter cubed each. And which electrode do we use? If we have only solutions in the equation, then my electrode has to be a platinum electrode. The standard reduction potentials of two systems are this. What is the value of the E cell for this reaction? Again, we use the values, but if we are inverting the reaction, we invert the sign of the electrode potential. So what do we have? We have tin 4 plus going to tin 2 plus. So that's the same as the one above. We have iron 3 in the data booklet. It's going to be iron 3 to iron 2. But what I want in the reaction is iron 2 going to iron 3. So I need to invert the sign for that electrode potential. Now, when we do this, of course, I always like to make sure my reactions are correct. So if you're going to add them all up, this will give the required reaction. Remember, electrons on both sides of the arrow have to be the same number, and then they are cancelled. The E cells, we said we're going to invert the sign for the one for iron 2 to iron 3. So the overall E of the cell is minus 0.62. Again, please do not forget to write the sign. The value of E cell of a reaction is positive. It can be deduced that what? If the E cell of a reaction is positive, remember we said the E cell, first of all, has to be positive for the reaction to be feasible. So if he's asking, is the reaction feasible? Yes, because the E cell is positive. But here we're asking, it is proportional to what? You should remember, the E naught of a cell is proportional to ln K, the natural log of the equilibrium constant. It's also proportional to delta S total. And you should know that if the E naught of a cell is positive, that means the delta S total is positive. So that is my choice. Okay. Some ionic half equations are given, so we have a table, and then the question says, use the data booklet to complete the table by giving both the ionic half equation for the system which has a standard electrode potential of plus 0.77 and the missing electrode potential value. So you just turn to the data booklet that will be given in the exam, and we look for which one has a reduction potential of plus 0.77. You'll find that it is the iron 3 plus going to iron 2 plus. Now look for the electrode potential of Cl2 going to Cl minus. You will find that it is plus 1.36. So we have filled the table. Then the question says, from the substances shown in the table, so this is the table now, select the species which is the most powerful reducing agent. Again, we said, where do we have the most powerful reducing agent? The one on top is the most powerful reducing agent, tends to lose electrons. So in the table, this is zinc. The species which in acidic solution will reduce VO2 plus to V3 plus, but will not reduce V3 plus to V2 plus. Again, we said the one that will reduce something has to be above it in the table. If it will not reduce it, then it is below it. So we're looking for VO2 plus going to V3 plus. We want that to be reduced, and that means the equation above it would do that. But I don't want V3 plus going to V2 plus, and that means it will have to be below that equation. So that is my sulfite ion. And we're going to stop here for this part of the video, and we will continue these questions in part 2.